Hello and welcome to another lesson. Now this is part of a sequence of lessons on electrons, and I've already done some lessons on the basis of an atom, better understanding an atom and isotopes and other things. So this sort of that you really should visit those ones first before you do anything. So this is one of these crazy things, and we're going to find out it's crazier than it sounds, but we're just going to treat it as a simple analogy, and we're just going to go through and look at it in terms of what you need to know. If you so desire, you can of course go on and do applied physics or theoretical physics at university level to whichever level you choose to do, and of course you will find out more and more about electrons if that's what you choose to chase. So let's look back what we saw. We've already seen that in our theory of the atom, originally we had this whole idea that we had these little balls, these indestructible balls, which basically could not be ripped apart, and all this was changed by that experiment by Thomson. Remember, he had the cathode ray tube, and he noticed that he could bend, similar to what I've got here. If he's got a positively charged plate, then he noticed these cathode rays bent towards that. That meant that these must be negatively charged because opposites attract, likes repel. So the movement of these negatively charged particles was his claim to fame. And he gave them the name of electrons, and that's where we start from. So this is a beam of particles he saw. There is evidence in this in certain cathode ray tubes which show that if cathode rays strike a bit of matter, they can cause it to move. That's pretty strong evidence for particles. More about that though in a subsequent session. Alright, then along came, as we saw, Rutherford, and he found out where these negatively charged electrons were. Remember, he fired the alpha particles, and he basically did the, if you like, the solar system model of the atom. He started thinking about it that ways, where we've got these positive charges in the middle, a lot of empty space, and the electrons moving around the positive charge. Alright, so then we developed from there. And the next dude who came along was a fellow by the name of Bohr, and he did lots of work that suggested that elements, or electrons, sorry, are actually in energy areas. He thought that they moved around in these energy orbitals. He still kept some of the planetary model, and these sort of things helped us understand what he was talking about. So let's not digress, but let's dig deeper. Now, we've all been to a fireworks display, and we've all seen these wonderful shades of different colours coming out. Now, all that is due to different elements. And as the elements are excited, the electrons in them move. Suddenly, they've got too much. Let's say we look at this series here. I'm not worried about the names on these series. That came with the piece of information I chose to use. But they do have names, and they do have different meanings about what goes on. Alright, so let's look at this one. So he said that when they were heated, like in fireworks, we're actually finding they would move up. But because they've been given extra energy, they don't like it, and so they release that energy and fall back to where they start from. So if they jump from 1 to 2, or our first energy level to our second energy level, when they fell back, they gave out this irradiation here. Now if they got even more energy, because remember we said electrons need more energy to get out to here, there is more energy involved in each one. This one is the lowest energy level, second lowest, third lowest, fourth lowest, etc. Alright, so as they go out, they actually lose energy when they come back. So they gain energy from heat, and that's how fireworks work. They gain energy, and they do this. Now, these things produce a pattern, and it looks very similar. I'm just going to quickly, it looks very similar to this sort of thing, where this is my red end of my spectrum, this is my violet end of my spectrum, and we get a pattern of lines. Now, your teacher might have shown you this, but if not, you might see it later on. You might see it in your senior chemistry or senior physics course, maybe year 11. Now, each one of the elements has got its own pattern. So it's like a set of fingerprints, if you like. And these are due to the electrons. So the electrons being hit with some energy, given extra energy than they wanted, moving somewhere, then releasing that energy, giving us these colours, or these patterns we see. Now, as you might learn in year 11, when you do work on astronomy, this is how we study the stars and how we work out what stars are made from. So all this material is linked. Okay? So we've got these electrons and we've got them in energy levels. That's what Bohr suggested. And this is why his theory has passed the test of time at that time. Now, after that, we move into more of the theoretical stuff. And you might have done some work in probability. Probability is the chance of something happening. Alright, so a fellow by the name of Schrodinger, you might have heard of Schrodinger's cat, and they talk about it being not knowing where it is, not knowing whether it's dead or alive at the same time. There is a very famous puzzle with that. But I'm not going to go into that one. I'm simply going to go into what we're doing here. Uncertainty meant that we knew electrons moved around the nucleus. We knew they moved randomly. We knew that electrons were unique and different. In other words, the electron that sits here is different from the electron that sits here. You can't have the same properties and all the same anything about them, otherwise they suddenly become the same thing. And they're so tiny, as we're going to find out, and that makes it really hard. And we know that the electron position is decided by its energy. All these things have come out. And again, here is this thing, here is the nucleus in the middle, and energy increases. The energy of the electrons increase. So this has got the lowest energy, that's the second lowest, and it keeps going. Now, I've only drawn two clouds or shells here. And our Schrodinger man, basically he used a bit of other information that came from very strong mathematicians at the time. And basically he said that if we go looking for an electron, we're not going to see it running around the track or the laps around the area, or like planets around the sun, our solar system model. No, they're just going to be randomly moving in that area. So in other words, the chances of finding an electron are higher in the cloud area. Now, chances of finding a cloud area here, but also the space between these clouds, and there is space between these clouds, empty space, the chances of finding an electron there are 0. So they were telling us that electrons can only exist in the clouds. They cannot exist between the clouds. Most interesting. But they also talk about other things, and if you delve into this in a lot more detail, which I'm not going to at the moment because I've designed these for basically upper middle years levels. Alright, so this is where we're up to, and this is our current, pretty much our current model, or the model we're going to be looking at. And that is where I'm going to stop this one, because it starts to get very, very complex now. And I'm going to try to break the complexity down a little bit and try to help you understand it. I hope this has been a good beginning.